refer you to this paper from 1949. B.H. Neumann constructed a biorderable infinitely generated group which is perfect. That is, it's equal to its commutator subgroup. Or in other words, it becomes trivial if you abelianize. This is not possible for finitely generated biordered groups. The finitely generated biordered group always has a quotient which is the integers. It's locally indicable. I didn't prove that in my notes, but it's true and non-trivial, but true. So this group is locally indicable. Any finitely generated subgroup will also again be biorderable and therefore have the integers as a quotient. But it's not indicable itself because any map to an abelian group will have to kill the commutators and therefore the whole group. Yeah. Okay, so this is my last lecture. Can I begin? Yeah. I'm now going to talk about, I'll remind you, we proved that every knot group is locally indicable and therefore left orderable. And in fact, the same is true of, more generally, of any link group. Uh-oh.
You can just touch the screen.
The theorem we proved about irreducible manifolds holds for non-split links, and if you have a split link, then the group is the free product of the various parts, and being locally indicable is also preserved under taking free products. So every link group, in fact, is locally indicable and therefore left orderable. Now today I'm going to talk about a special case of fibred knots, which is, the reason I'm doing that is because it's the only category of knots that I know of where I can prove biorderable, that the group is biorderable. And so let me just outline. We know that every knot, for example, the trefoil bounds an orientable surface. For example, if I draw this, it's kind of like a soap film, maybe red on one side and blue on the other side. And these little twists here, it's kind of a ribbon that twists around. So it's a two-sided surface bounded by a knot. That can be done for any knot whatsoever, or indeed any link. But a very special kind of knot is when you have a whole family of such surfaces that sweep out the entire complement in a circular manner. Whoops, wrong way. So we say the knot is fibred. This was discovered by Neuwirth, and Stallings sometime in the 60s, I believe, that certain knots complements could be fibred over a circle. Let's see. It doesn't show up, the pointer. My battery's weak. Okay, anyway. If you have a bundle map from the knot complement to the circle in which the fibers are open surfaces like this, whose closures actually have the knot as the boundary, then we call that a fibred knot. For example, all torus knots. This is a fibered knot. The figure 8 knot, which I think I drew on Wednesday, is also a fibered knot, but not every knot is a fibered knot. In fact, the majority of them are not. No pun intended. So in other words, the complement of the knot is filled up with a circle's worth of orientable surfaces disjoint. But of course, as the circles sweep around, you can think of it as the product of the knot complement with an interval, but the top and bottom are, I'll get to that in a minute. I want to remind you, if you have a fiber bundle, so X is the total space, F is the fiber, and in this case, S1 is the base, there's a long exact homotopy sequence associated with that. This is induced by inclusion, even for pi n, and this is the projection, and then there's a boundary map that goes from the base to the fiber in one dimension lower. But it happens that so it would be pi 2 of S1 here, but that's trivial. And down here with pi 0 of the F, it's a connected fiber. So it's a short exact sequence. And actually, before I knew that all knot groups were locally indicable, there's a very easy proof for fibered knots, because this is a free group. It's pi 1 of a surface without boundary. It's free with 2 G generators, where G is the surface. This is a free group on one generator, free Abelian, infinite cyclic. And by the extension property, which I gave as an exercise, it's called exercise 4 in the notes, since these two guys are locally indicable, this is locally indicable. So for fibered knots, it's a very short argument. Another way of looking at fibrations over a circle is if you think of just cutting the circle open and getting an interval, you can think of it as a fiber cross an interval in which one end is glued to the other end. So the pair x1 on that end is paired with h of x0, where h is some homeomorphism of the fiber. And it's sometimes called monodromy. It's a much misused word, but anyway, that's what I'll call it. And if you look at the monodromy on the level of homology, this is integer coefficients, or let's take rational coefficients, because we want to do some linear algebra with it. You can take, or even complex coefficients. If you look at the monodromy here, this is a linear transformation. And this is a vector space if you take real or complex coefficients, which you might as well do. And then take its characteristic polynomial. That's nothing more than the so-called Alexander polynomial. Now, non-fibered knots also have an Alexander polynomial, which is defined in a little more complicated way, that happens to coincide, in this case, with the characteristic polynomial of the monodromy. So there are knots that have Alexander polynomials that are not monic. That is, the leading coefficient need not be 1 in general, but for fibered knots, it's a monic polynomial. Also, the group of a fibered knot can be thought of from this equation. You can think of it as the group of F. If you multiply with an interval, it still has the same fundamental group, but then we are gluing the top and bottom together, and that's reflected algebraically by what's called an HNN extension, Higman, Neumann, Neumann. this Neumann and his wife, or the two Neumanns. By the way, their son is a professor in New York, Columbia. Walter Neumann, the child of this guy and Hannah Neumann. Yeah. And the HNN extension, in this case, we just have the free group generated by 2G generators. Then you have one more generator that corresponds to the circle direction, the base, or the interval. And the image of each generator is declared to be the conjugate of itself by that new generator T. This, in fact, is what gives you the fundamental group of the total space of a fibration. Now, if we want to bi-order such a group, that will be possible. The free groups are bi-orderable. We'll prove that in a few minutes. And if you have this relation, you see, in order for this HNN extension to be bi-orderable, it's necessary that H star preserve an order, some ordering of the free group, because it's going to be a conjugate of a generator. And if the generator is positive, then the conjugate has to be positive. And so H star will have to preserve the positive cone, and that's equivalent to preserving the ordering. In other words, H star of X is less than H star of Y if and only if X is less than Y. Okay, so I'm assigning that as an exercise. And now there's two proofs regarding bi-ordering of fibered knot groups. Both of them I've been involved in. The first one was proved about 7 years ago with Bernard Perron, who is, he's passed away now, but he was at the university in Dijon, France, and he really helped me with the algebra necessary for this. I'll get to that in a minute. And then there's a sort of partial converse. So this result says that if you have a fibered knot and its Alexander polynomial has all roots real and positive, then you can bi-order its group. And I don't know if the converse is true. That is, if a group is bi-orderable, are all the roots real and positive, but there's a partial converse due to myself and my student Adam Clay, that if a knot's fibered and its group is, bi-orderable, then you have to have at least one real positive root. In fact, you need to have two, because Alexander polynomial has a symmetry that delta k of 1 over t equals delta k of t, maybe times some power of t. So if you have a positive root, then 1 over that is also a root. So the roots come in pairs, reciprocal pairs. So it has to have at least two positive roots. One cannot be a root. Delta of 1 is never 0. Delta of 1 is 1, in fact. Okay, so before getting to sketch, I'm just going to sketch the proofs of these because they're a little bit involved, and I'll just hit on the basic key ideas. But first, let's look at some applications, some examples. One observation, which I meant to say previously, but I didn't. Another special property of bi-orderable groups is if you have an element commuting with the power of another element, then it has to commute with that element itself. That's not true in general for groups or even for left-orderable groups, but it is true for biorderable groups. I'm leaving as an exercise, but there's a hint here. Compared H with the conjugate of H by G. And recall that in biordered groups you can multiply inequalities. So more generally, if two elements have powers that commute, pth power and qth power, then the elements themselves have to commute. That actually follows formally from the first statement. So now torus knots, I mentioned this is one example. Those are knots which can be drawn on the surface of a donut, a standardly embedded donut. Like that. There are infinitely many of them. They're parameterized by relatively prime pairs of integers, p and q. And their group, the fundamental group, you can just calculate from, you take a generator, let's say A inside and B outside, which is again a solid torus. And then with Van Kampen's theorem, you get this relation, A to the P equals B to the Q. Very simple presentation for the group. And since that's a knot group, it's a locally indicable group, but it can't be biordered, right? Because A commutes with B to the Q, because B to the Q is a power of A. A certainly commutes with the power of itself. But it doesn't commute with B unless, if it did, then this group would be abelian. And the only abelian knot groups is the integers, the group of the trivial knot. That's a classical result also. So this shows that the group of a non-trivial torus knot cannot be biordered. Now let's look at the figure 8 knot. This is really the next non-trivial knot in the standard knot tables. It's the only knot with 4 crossings and is a minimal projection. It's fibred, and its Alexander polynomial is this, t squared minus 3t plus 1, using the binomial, not binomial theorem, the, what's it called? The quadratic formula. You can find the roots are 3 plus or minus root 5 over 2, real positive numbers. So we conclude that the group of the knot 4-1 is biorderable. I was quite excited when we found that out because a lot of people were asking, well, we know we can left order knot groups, can we biorder any of them? And so the answer is yes. There are other examples that also have all the roots positive, but they're fairly unusual. Here's one, the knot 8-12. This polynomial has 4 roots, all real and positive. Here's another one of degree 4. Here's another one of degree 6. This is degree 4. Some 12 crossing knots. These all have biordered group, and they're fibred.
Are they all fibred or?
Sorry?
Are they fibred?
They are fibred, yeah. There's a lovely computer, a website called Knot.info, which J2 Cha is one of the maintainers of, and it tells you which of these knots are fibred. I'm not sure how they determine it, but and Chuck Livingston's the other maintainer of that. So these all have the same degree 4 polynomial, but they're different knots. I believe that's the complete list of knots up to 12 crossings that I know have biordered fundamental groups. Now the converse, or the partial converse, the second theorem, was that if the knot group is biordered, then there has to be at least one In fact, 2 positive real roots. We could use that to give another proof that the torus knots are non-biorderable, because we know they're polynomial. Whoops. This looks like a rational function, but in fact it's a polynomial. And the roots are on the unit circle of the complex plane. They're pq roots of unity, which are not p roots of unity or q roots of unity or 1. So they're distributed around on the unit circle, and none of them are real. So that's another proof that torus knot groups are not biorderable. A lot more complicated than the one I just discussed, however. And I'm now going to give you a list of the non-biorderable knot groups, again, of fibred knots. I guess you see them in front of you. Lots more. Okay. This is my student Adam Clay went through all the fibred knots of up to 12 crossings and worked out the polynomials using maple, found the roots, and found that none of them had real roots, positive real roots. Okay. So now let's look at the proofs. The first theorem was, well, abbreviated, if all the roots of the Alexander polynomial are positive, then the knot group is biorderable. Now, to motivate the proof, let's do a little linear algebra. Suppose you have an upper triangular matrix with eigenvalues lambda 1, lambda 2, lambda 3, and look at its product with an arbitrary vector. You get lambda 1 x1 plus stuff, lambda 2 x2 plus stuff, lambda 3 x3. Now I claim that if these lambdas are positive, then I can biorder R3 in this case in such a way I can get an invariant ordering of R3, which is also invariant under this matrix. The way you do that is declare a vector to be positive. It's a lexicographic ordering, but reverse. You look at the last, not the first, but the last non-zero entry, and if it's greater than 0, we say that it's a positive vector. And then you can easily check that if these numbers are positive real, and this is a positive vector in that sense, then so is the image, because the lambdas are positive. So more generally, if you have a linear transformation, all of its eigenvalues are positive. So this L is a linear map from Rn to itself. If the eigenvalues are real and positive, then you can biorder Rn to be invariant under L. It's essentially this proof. You can use Jordan canonical form or whatever. You can conjugate it to an upper triangular matrix with eigenvalues on the diagonal, and then order it in such a way. So you choose a basis of eigenvectors, and then lexicographically order in reverse lex order, basically. So remember, the group was a HNN extension. Yes?
In the previous slide, what happens if L does not have an eigenvalue in real number? What happens if L does not have an eigenvalue in real?
Yeah.
And how can you say that L preserves the order of Rn?
Well, you may not. I'd say if they all are real and positive, then you have a, yeah. No, for example, suppose you have a rotation of the plane by, let's say, 60 degrees, so that it has order 6. There's no way to have an invariant ordering of that rotation, because if something's positive after 3 rotations, it'll be its negative. So, in fact, you can't have a periodic linear transformation preserve an order. It's a special property. And one thing that guarantees it is that the eigenvalues are all positive. So remember what we needed to have for biordering the knot group, which is an HNN extension. We needed a biordering of pi1. Now, there's a little confusion here. F is now the fundamental group of the surface, which I also called F. But here it's a free group. So, proposition, we have a finally generated free group, an automorphism of it. And if all the eigenvalues of the homology induced map of that automorphism are real and positive, then I claim there's a biordering of F preserved by H, which is what we need. Now, how do we biorder a free group? There are various ways, uncountably many ways, in fact. But one way to do it is to use the lower central series. It's a descending series of subgroups of F. The first one is F itself. And then the I plus first one is the group generated by commutators of the previous one with elements of F. That's a famous construction in group theory. If that ever terminates in a finite amount of time, or for some finite I, then it's called a nilpotent group of certain index. For free groups, they're residually nilpotent. That is, the intersection over all of them is the identity. Every non-identity element eventually gets excluded in the lower central series. And the quotients are free abelian. There's no torsion. They're abelian groups just from construction, but they're free abelian groups in the case of a free group. I think also for right-angled Artin groups, same thing is true. That's why those are biorderable. Anyway, free groups. We have this property, these two properties of the lower central series, and we can use that to biorder the free group. Since this is free abelian, it's essentially Z to some power, we can certainly biorder that any way we like. So choose an arbitrary ordering of the quotient, and now to define a positive cone for F, take a non-identity element and call it positive if in the last I in which X lives is positive in that quotient. So it's a sort of lexicographic order in the series of lower central quotients. Okay, so no matter how you choose a biordering in each of these, this definition will give, there's some work involved to check that it's invariant under conjugation and so on, but it's pretty routine. That gives a biordering of the free group. Now if we want one moreover that's invariant under an automorphism, then we want to get biorderings of these groups, which are also invariant under the automorphism induced. So you notice if you have an automorphism of the group, it will take, just by definition of the lower central series, the image of Fi under H will lie in Fi. It'll again be a commutator. And so you get induced maps of the lower central quotients. I'm going to call that HI. And so what we really want now is to, and H1 is just what you call the Abelianization. That's F modulo its commutator subgroup. We want to have orderings of these free abelian groups invariant under the HI. And this is where I kind of gave up until Bernard Perron pointed out that, well, really, these things are basically determined by the first one, the Abelianization. And there's an algebraic trick in which you can embed these lower central quotients in the tensor power of the Abelianization, which is an abelian group, the kth tensor power, and under that embedding, the map HI is just the Abelianization tensor power of itself, restricted to the image of that embedding. Now, I won't go into the details of how you embed that. It's fairly straightforward if you're an algebraist, I guess. But now, remember, we're assuming that all the eigenvalues of the Abelianization are real and positive. Well, the eigenvalues of a tensor power are just powers of the products of the original. If they were all real and positive, so are all their products. So it's sort of a miracle. We get all the tensor powers have real positive eigenvalues, and therefore so do the restrictions to the to the embeddings of this. So that allows us to find biorderings of each of these free abelian groups invariant under the HI. And then because of that, we use those particular biorderings to biorder F by the formula I mentioned before, lexicographic, and that proves the proposition and therefore the theorem that we have an biordering of the free group invariant under the homotopy monodromy, which is what we needed. And this all comes from the Alexander polynomial. Okay, any questions on that? Now let's look at the second theorem, the one with Adam Clay. That says that if the knot is fibred and its group is biorderable, then the Alexander polynomial has at least one positive root. Well, we're going to use another theorem that we had to prove to do this, and that is if you have any, in fact, non-trivial finitely generated biordered group and an automorphism preserving the biordering, then the induced map has to have at least one positive eigenvalue. So remember, this for the free group, the group of the fiber, is just the homology monodromy, which, and its eigenvalues are exactly the roots of the Alexander polynomial. So we kicked this around a lot, and I'm not going to go into all the details. We have some short exact sequences to deal with, but the key idea is to consider a linear automorphism of rational vector space of finite dimension, q to the n, and suppose that preserves an ordering. I want to be able to conclude then that it has a positive real eigenvalue. Well, if you regard Qn as a subset of R to the n in a natural way, you can define the set of all points in R to the n, so that every neighborhood of X contains both positive and negative points under that chosen ordering, right?
How do we know that H is non-empty?
That what is, that H is not empty?
Oh, okay, basic hyperplane. So you think of plane and you
You have to prove that it's a hyperplane.
Yeah.
You look at all points that have both positive and negative elements in a neighborhood. First of all, the origin has to have that.
Yeah.
And then you show that if that it's a linear space, that the sum of 2 points with this property, if each of them has positive and negative points in every neighborhood, then so does their sum. So does any positive or negative power. So you get that it's actually a linear subspace.
What I'm thinking is that if you think of a plane and the line with irrational slope,
Yeah.
and this side one part is particle, then in that case H should be empty, 1 point.
No, we're in Rn, not Qn. Oops, what did I?
Okay, right.
Oops. Yeah, that's where I'm in Rn. This may not intersect any rational points except the origin.
Yeah.
But I've passed to the algebraic closure, so to speak. And H separates Rn. On one side, you'll have all the guys who are positive in that order, and on the other side, negative. Well, the fact that this is a hyperplane requires some delta epsilon arguments, but it's true. And if you're really interested, I have a reprint I can supply the details with. It's also clearly invariant under L because L, by assumption, we had an ordering that's preserved by L, so the positive guys go to positive guys, negative go to negative, so that hyperplane is preserved by L. And so are the two sides. And now a standard argument, it's similar to the Perron-Frobenius theorem, different Perron. Look at the unit sphere in Rn. So we had this hyperplane, which is invariant, and now look at the unit sphere and take the disk, which is on the positive side. It's a hemisphere. And then there's a mapping of D that comes from L. You just look at the image you look at L of X and normalize it to give it unit length again. So that takes the unit sphere to itself, because if X is positive, so is L of X, and so is the normalization. It's also on the positive side. So it's a mapping D to D. Well, there's a famous theorem, one of my favorite topology theorems. D is an n-1 disk, or ball. And so the Brouwer fixed point theorem implies that there has to be a fixed point of this mapping. That says that there exists X such that L of X is in the same direction. In other words, that would be an eigenvector and with a positive eigenvalue. So, positive real eigenvalue. So that's the key idea in the proof. And now I'm going to just, I'll probably end early. That's what happens with slides. You can go through things a lot faster than when you write. One reason that I'm interested in knot theory is because of the applications of knot theory to three manifolds. There are various ways of relating knots to three manifolds. One is to look at branched covers, but maybe the more important one is surgery on a knot. Well, the process of surgery is to remove a tubular neighborhood of the knot, and then what you've removed is a solid torus, topologically just a circle across a disk. But then there are different ways of reattaching it to that torus which is left there. And it's actually specified by a curve on the boundary of that neighborhood. Let's see, I have a picture coming up here. Yep, whoop, there. Here's an example. Here's a trefoil knot. This dark curve is a curve on the boundary which is not a meridian. Meridian would be the one that just goes around this way, and it's not a longitude. In fact, it has linking number +1. So that would be called a +1 framing. But in general, you can get framings like this, a PQ framing, and the surgery described by that curve, let's get back to, oops. So you take what's called a meridian here, which is something on the solid torus, which bounds a disk in the solid torus, and you attach the solid torus so that that blue curve goes to the specified framing curve on the target, and that's a process called surgery, three-dimensional surgery. This was used by Max Dane way back in the early 1900s to give an alternative construction of Poincaré's homology sphere. It's a sphere that has, a three-manifold, compact three-manifold with the same homology as S3, but a non-trivial fundamental group. And Max Dane's construction shows you how to construct buckets and buckets of them, infinitely many, by surgery on a knot. Even on a trefoil, you can get infinitely many surgeries that give you homology spheres, but with non-trivial fundamental groups. I just want to point out that a famous theorem of Wallace and independently Licorice is that all compact orientable three-manifolds arise by surgery, not necessarily in a knot, but on a link, a disjoint union of knots in S3. So knot theory is really important in understanding three manifolds through this construction and through similar constructions. So let's look at this particular example. This is Dane's construction. I should apologize that these x's and y's do not correspond to the x's and y's on the group. I think the y corresponds to the x and the x corresponds to something else. But anyway, the group has a presentation with two generators and two relations, like that. If you Abelianize this, you conclude quite easily that it becomes trivial. So that means that this has the homology of a sphere, but it's a non-trivial group. In fact, it's a finite group of order 120. So it's certainly not a left orderable group. So it's clear that if you do surgery on a knot, which has left orderable group, well, what you're really doing is you're looking at a quotient. You're killing the attaching curve. That's exactly how you compute the fundamental group of the surgery manifold. And you do not preserve orderability. But you might. I'm going to give another example, but I need to have a bit of an aside here. interesting group called SL2R tilde. And it's one of the Thurston three-manifold geometries, one of the more unusual ones. But let me just explain it briefly. The matrix group SL2R acts on the circle. Many ways of seeing that. You can take a unit vector in the plane and hit it by a matrix. What is SL2R? It's 2 by 2 matrices with determinant 1. It acts on the circle by taking a unit vector to some other vector and then normalizing it. Or another way of seeing it is to look at fractional linear transformations, Mobius transformations. And they're defined for complex matrices, but the real matrices preserve the real line, obviously, and they also preserve the upper half plane. In fact, it's the group of isometries of the hyperbolic space. So it preserves this circle. In fact, the circle is a compactified real line. It takes, you have to throw infinity in there in order to make it well defined, because it's a fractional linear transformation. If you get 0 in the denominator, you call the result infinite. And it preserves orientation. It takes the line to the line, takes the upper half plane to the upper half plane, so it can't reverse orientation of the line. Well, it doesn't, let's put it that way. It could, I guess. There's also a topology. SL2R has 4 coordinates, 4 real coordinates, so you can just look at it as a subset of R4. And as such, it actually has the homotopy type of a circle. It's a circle, it's a solid torus, actually. Circle across a disk. And its universal cover, therefore, is infinite cyclic, right? It has infinite cyclic fundamental group, so universal covering is a non-compact space with the integers acting on it, but it also has a group structure which you can define. And as a group, it acts on not S1 but R1, the reals, by orientation preserving homeomorphisms. Well, that means that it's a subgroup in a natural way of homeo plus of R. Right? It acts on universal cover by orientation preserving homeomorphisms. Anything that's not the identity acts non-trivially. So it's actually a subgroup of homeo plus R. And therefore, because we know that this is left orderable, conclude that this is also left orderable. Yeah?
The group SL2R tilde is countable.
It's uncountable.
Uncountable.
Yeah. It's an uncountable group. SL2R itself is uncountable, and it's a covering of that. Now let's look at the trefoil, and instead of doing +1 framing, let's do -1 framing. And if you compute the fundamental group of the resulting 3-manifold, again you get a homology sphere, and the fundamental group is almost identical except the 5 turns into a 7. For those in the know, this is also a Breeze-Korn manifold 237. Well, in a paper of 1990, I believe, George Bergman observed, he actually explicitly showed how to map this group into this covering group of the matrix group in a very explicit way. And show that it actually maps injectively. I think Bill Thurston knew this also, but didn't bother to write it down. George Bergman did. And that was the first published example of a left orderable group which is not locally indicable. So this 3-manifold, whoops, is left orderable. Why? Because its group embeds in SL2R, which is left orderable. But its first Betti number is 0 because it's a homology sphere. So there are left orderable 3-manifold groups which are perfect. Right, that's a perfect group. So, whoops, because it's perfect, it's not biorderable or even locally indicable, because perfect groups can never be mapping to the integers. And it's finitely generated, 2 generators. Okay. Now, let's look at some applications of biorderability to surgery. This is a theorem of Adam Clay and myself. Sort of follows from our calculations, from our conclusion for fibred knots having, if they're biordered, then they have positive real roots. So if you have a fibred knot and you get a biorderable fundamental group by surgery on the knot, non-trivial surgery. If you do a trivial surgery, you just sew the torus back to where it was and you get S3, which has trivial fundamental group, which some people don't consider biorderable, some people do. But let's say we have non-trivial surgery, you get a 3-manifold whose group is biorderable. Then it has to be a very special surgery that is 0 framed. That's actually true for any knot, just a homology calculation. It's the only way you get infinite homology, is to do 0 frame surgery, and the Alexander polynomial has to have a positive real root. And moreover, in that case, the surgery manifold itself, the fibration of the knot complement extends to the manifold. That's fairly easy to see with 0 frame surgery. So again, a connection between orderability, positive roots, and orderability of the surgery manifold. And now I'm going to end with some fairly recent phenomenon. Osvath and Szabo devised this very powerful theory called Heegard-Floer homology. There's actually several flavors of it. This is the hat flavor, HF hat of M. And they define an L space to be a rational homology sphere, a 3-manifold whose first homology over the rationals is trivial. So for example, if the first homology is finite, then over the rationals it becomes 0. And if its Heegard-Floer homology is as simple as possible, in general, Heegard-Floer homology group has rank, it's an abelian group of rank at least this, but if it's equal to just that, the rank of the first homology with integer coefficients, not the rank, the cardinality, this will be a finite group. So, for example, lens spaces, or more generally 3-manifolds with finite fundamental group, are L spaces. But there are a lot of L spaces with infinite fundamental group also. And Adam and I showed that if you do surgery on a knot, any knot, and you get an L space, then the knot group cannot be biorderable. Or another way of saying is, if you do have a biordering of your knot group, as in some of those examples I flashed before, you'll never get L space by doing surgery on the knot.
This question does
Yeah.
surgery means that there is a surgery or every surgery?
If there's any surgery that results in an L space, then the knot group cannot be bi-ordered. Yeah. Now, the proof is got several steps. First of all, Yi, is that how you pronounce it? It's a Chinese name. Anyway, he showed that if you get an L space surgery on a knot, then the knot has to be fibred. That's good news because our results only apply to fibred knots. And then Osvath and Szabo showed that if you do L space surgery, then the Alexander polynomial has a very special form. In particular, all the coefficients are plus or minus 1 or 0. And then we just argue that any polynomial of that form cannot have positive real roots. So that means that the knot group can't be bi-ordered. And I think that's the end. Thank you very much for your attention.